Welcome, everybody. This is the short time during this conference that I could put on my day job hat on for an hour and talk about AWS. Most of this conference, I put my community hat on and try to help arrange this thing. So you'll see me running around a lot, and I'll take off my nice shirt and put on a t-shirt as I move around boxes the rest of the week. But I'm Jim Mlodgenski. I'm a database engineer, part of the Aurora and RDS Postgres teams. And we'll talk a little bit about Aurora, go deeper, a little deeper than what Kevin just did, and then end it off with some brief stuff about performance, but we'll let Jim Finnerty after me go a lot deeper on the performance aspect of it, but we'll just try to build on it throughout the course of the day. That's kind of what we're trying to do today, is educate everybody about Postgres in the AWS world, leading up to this afternoon of how people are using it. So one of the things that I know at least I do is from the vernacular standpoint, I talk about Aurora and RDS. Right? It's really, Aurora is part of RDS. It's one of the main engines of RDS. It's part of the same platform. But just in order to distinguish between RDS Postgres and Aurora Postgres, I end up calling it RDS and Aurora. A lot of folks at AWS do the same thing, and it's kind of just in the vernacular of everybody. But Aurora is part of RDS. So all the same tools apply. Your same console and everything works. But it's just part of the same family that's there. But we'll mix the terms a bit, and throughout the course of today, you'll hear it say RDS, and that means RDS Postgres, which is a lot closer to the community, versus Aurora Postgres, which has the Aurora storage underneath it. So one of the questions that got asked at the end of Kevin's presentation is, what's the difference? We talked briefly about some of them, but when you're making the decision, you have RDS Postgres sitting on top of EBS volumes, Aurora Postgres sitting on top of Aurora storage. But from your application, they're going to look the same, right? You're going to connect with the same JDBC drivers, ODBC drivers, pSQL. It's going to look like a regular Postgres database. It's going to give you the same backup and restore capabilities, point-in-time recovery. Even though Aurora Postgres will do it in a different manner, you have that same capabilities. Same thing with high durability and high availability. Aurora is built to give you higher availability and higher durability, but you're able to get it in both of them. From security, from doing things like IAM authentication. So if you have higher security environments, allows you to be able to log in without passwords by getting a token that's only alive for 15 minutes. Same thing with replicas, cross-region snapshots and scaling out. Two of the things that aren't there in Aurora Postgres yet is cross-region replication and outbound logical replication. So if you want to be able to replicate your database from the East Coast to the West Coast, it's not there yet in Aurora Postgres. It's on its way. Same thing with outbound logical replication. As Kevin talked about in his presentation of being able to have replication outside of Aurora, that's also not quite there yet, but it's also on its way. But those are a couple of the differences between the two today. Right? And the idea is to have them in parity. We have Postgres 10 and Postgres 11, as Kevin just got announced last week, got released last week. So you have Postgres 11.1 available in RDS Postgres. So it's no longer in preview, it's in GA. So Aurora storage is log-based storage. What that means is, as you're making your writes, you're just sending your transaction logs. Right? So that gives us a lot of advantages. One of it, when you have a traditional database, when you're talking about Postgres, other databases, as you have a bunch of work to do, it goes into a queue, goes into a log buffer. Right? And that log buffer has to flush out the disk. You have to f-sync it in order to be durable. Right? So when you have as you're having more and more data flowing in, more and more transactions, in a group commit scenario where you have a lot of concurrent transactions going on, what happens is that log buffer gets full, and you have to wait in order to flush it out to disk in order to be able to go to do the next amount of work. So it has to flush out, be able to fsync, and then come back and do more work. One of the advantages of the architecture of Aurora storage, we don't have that same bottleneck, right? What it is you have each one of the transactions, what it's going to do as it's ready, it's just going to flush things out the storage, right? So this way you have multiple things, you have 5 different transactions, all as they're ready, flushing everything out the storage. But we're keeping track of the durability, right? As Kevin mentioned in his talk, we need 4 of 6 quorum for durability. So when 4 of the 6 storage nodes come back and say that this is it's durable, it's going to be able to acknowledge the commit back to the client. And we're going to go a little bit deeper about storage nodes and how that works. But at first, nobody came back and said, we're durable yet. We just flushed out those 5 transactions. But after you wait a little bit, fractions of a millisecond, 2 of the 6 came back for transactions A and B. So it's almost there, it's halfway done. Right? Then you wait a little bit longer, transaction A hits 4. It's good, it's durable, it's across 4 of the 6. But if you notice, C also has it 4, but we haven't acknowledged that back to the client. Postgres is a ACID compliant relational database. Everything has to happen in a specific order. So we can't acknowledge it until B has been also there. So it has to go in order. Right? So it's going to wait in order to acknowledge C has gone back to the client until B is also done. So if you wait a little longer, then you're going to see that B and C also get acknowledged. They're durable. They hit their 4 or 6 quorum. And also E is also at 5, but we also have to wait there because D isn't quite at the 4 of 6 yet. So this way, each transaction, as it's ready to flush out the storage, it just goes ahead and does that. There's no waiting for the log buffers, waiting for everybody to fsync on that same transaction log volume. One of the other big advantages of Aurora Postgres is we write a lot less. So in a traditional database, you have to do things called checkpointing. And what a checkpoint is making sure that all your changes that that you made recently in your database that you've written out to your transaction log are flushed out to the main data files themselves. Otherwise, you're going to have a really long time there for recovery trying to replay all your transaction logs. So periodically, you have to do that. And in Postgres, you end up doing extra work when you're doing that called full page writes, and we'll get into that. So if you're writing something in Postgres, you're going to do an update. And one of the things about Postgres with multi-version concurrency control, so different transactions are not waiting on each other, where you have locking, an update in Postgres is a logical deletion of the old version and inserting a new one. So every update really is affecting 2 different rows. Right? That's written to the transaction log, and we're getting that full page. After a checkpoint, Postgres has to write out the full page out to the transaction log, and we'll get into that in a second, why we need to do that. But then after that, we insert a new row that gets written out to the transaction log, right? And then we do our checkpoint, flushing out to the data file. So we want to be able to write that page actually down to the data file itself on the storage, right? Also, what we want to be able to archive that log, being able to push that out so that in the event for point-in-time recovery, we want to be able to get that log file back. We could roll forward to any point in time since our backups, and that's pushed out to S3. But one of the things of why we need that full page write is just the mismatch between Linux and Postgres. Postgres writes everything in 8K pages. Linux writes everything in 4K pages. In the event that there's an error or a crash in the middle of flushing out that page, you get what's called a torn page. 4 of that 8K might have been written out to disk. So this way, in that event, your database would be corrupted, or at least that page would be corrupted. So what Postgres does in the event of a recovery, it takes that full page that's written to the transaction log and overwrites that entire page in a recovery scenario. So this way you don't get any torn page scenarios. Right? In Aurora, we update that row. We need to get those 2 versions of the row, just like any update. Aurora Postgres works the same as Postgres in that effect with multi-version concurrency control. And that's going to be important when we talk about vacuum in a little while. right? And that's flushed out to Aurora storage. You don't need that full page write because Aurora doesn't do any checkpoints. All that work is pushed down into the storage nodes themselves, right? And then we just happily go along, add that next row. We'll flush out Aurora storage out to S3 for backups, but there's no checkpoints, and because of no checkpoints, we don't need to do full page writes. It's one of the ways that we get higher throughput as your application is running. You're just writing a lot less to storage with Aurora as opposed to what you're doing with RDS Postgres or Community Postgres. So what happens inside the storage nodes? So we talked about that Aurora, you have 4 or 6 quorum. So on a very small database, you might be across 6 different storage nodes. Big databases, you might be across hundreds or even potentially thousands of different storage nodes. And this is what happens inside one of those. Right? So when an Aurora read-write node goes and makes a change, right, it flows into an incoming queue, and that's in memory. Right? It then goes into the update queue where it's persisted to storage. Right? At that point, it's durable, and it could acknowledge back. So that's the entire aspect that's synchronous, waiting for that acknowledgement back from the individual storage nodes. When you're waiting for that 4 or 6 quorum, it's coming into that queue, flushing it out to the update queue, so it's persistent on storage, and then you get the acknowledgement back. You are persistent on disk at that point. And behind the scenes, that update queue goes and does some extra work, asynchronously, that you don't have to wait for. It's just going to be doing things behind it because it's intelligent. It understands the wall format. It's doing things. It's writing out that update to the data blocks. Because when you need to do a read, you need to return back those data blocks. Right? So it's going to coalesce those changes into the individual data blocks. Right? It's also going out to the hot log, where their most recent changes. One of the advantages of the Aurora storage is with that 4 or 6 quorum, the different storage nodes use peer-to-peer gossip in order to be able to fix one another. So the event that you don't have to coordinate that from the main Postgres engine, the individual storage nodes fix themselves in the event of any sort of errors. And that hot log pushes stuff out into the individual pieces. Right? And all of that is pushed out to S3 for storage all the time. So you don't have to create a backup window or anything like that. Everything's being backed up automatically for you behind the scenes into S3. One of the differences between Aurora Postgres and RDS Postgres, you have to give it a backup window. Aurora Postgres, it's always backing up. So this way, when you do an individual read request, it's pulling it back that data block, which has been coalesced from the changes that's been pushed in there. So just to show some of the differences here of that and how you get additional throughput. We created a test table that has a bunch of different type of data in there, nine different columns, right? With just random things that are in there. We indexed every column, right? That might be not something that you would ordinarily do, but you might have 50 or 75 columns in there, and you might have 9 indexes on there, right? You might have 30 indexes on there. Not uncommon to see many indexes on wider tables, but just creating a large number of indexes on a fairly straightforward table. What we did is we did an insert workload test, right? And across the y-axis is the insert per second, and it's just time across the x-axis. And what you see with Postgres, with base Postgres, it starts out running pretty fast at around 25,000 inserts per second. Pretty fast, but it drops off radically, very quickly. Right? It's a very steep drop. And what's happening there is as your indexes are getting bigger and bigger, you're doing more full page writes. As you're checkpointing, you're going to have to do more and more work in order to be able to maintain that. Right? So it drops off radically as you have to do all those full page writes, because you have to do that not just for the main table, you have to do that for every index that you're maintaining. Right? So one of the things that DBAs typically do when they have to go through a lot of transaction logs, they increase the size of their transaction logs. So this way you spread out those checkpoints more. So increasing your transaction log size, your wall size, the write-ahead log, out to 16 gigabytes from the default of 2, right? It chugged along fine for about 20 minutes, right around 25,000 TPS, and then you saw that drop off again, right? You started getting that same sort of effect. But Aurora is across the top. It was a little bit more than it's about 27,000 TPS or so, but it was consistent. You're not doing those full page writes, right? So this way you're not getting that jitter or that massive drop off of having to be able to write that additional work out to storage because Aurora doesn't need to. And looking at it for the same thing of updating, right? So if you're updating 2 columns, you see that standard Postgres or RDS Postgres at 3,700 TPS, whereas in Aurora Postgres at 17,000. You see that same effect in updates as well, because an update, again, is a logical deletion and then inserting a new version of the row in Postgres. So you get that same effect that every time you do an update, it has to be able to insert new things into an index. But like I mentioned, one of the standard things that DBAs do in order to get higher throughput is to increase your transaction log size, right? In order to be able to spread out those checkpoints, right? But that comes as a trade-off. Whenever you're going to increase that transaction log size, you have the expense of recovery time. So in the event that server crashes for whatever reason, or if you even simply do a restart of the server because you want to change some parameters that require a restart, you have to be able to shut everything down, checkpoint everything out, and the longer there is, the longer it takes to be able to do that. So if we're doing a simple test here where we have 3 gigabyte of redo or wall, right, it'll go through at about 18,000 writes per second, which is along the x-axis here, and it'll have a recovery time of 19 seconds. So if your SLAs for getting that up after some sort of crash is really low, great. But you're giving up a lot of performance of only getting about 18,000 writes per second. You can increase that, make that size bigger, more about 10 gig. Right? But when you're doing that, you're going to get 37,000 or so writes per second at the trade of your recovery time. Now your recovery time went from 19 seconds out to 50 seconds. You go even further of making that 30 gigabytes, right? You get even more performance up around over 40,000 writes per second. But now your recovery time is up over 2 minutes, right? So it's one of the unfortunate things when you have databases that do the checkpoint, you're trying to balance performance versus your SLAs out to your customers, right? You're not making a technical decision, you're making a business decision in order to how to be able to maintain your database, right? But that little dot out in the corner that's kind of hard to see is Aurora. Because there's no redo, right? Recovery time only takes 3 seconds because there's nothing that has to go through recovery, right? And you're doing 135,000 transactions per second. Because you don't have that checkpointing, the full page writes, you're able to get that higher throughput, and you don't have to be able to trade your business rules for the recovery times. So let's talk a little bit more about the base architecture. We've talked about storage nodes in the 406 quorum. What does that mean? So whenever you create a new instance of Aurora, it's spread across 3 availability zones. So we're talking about Aurora storage, you want to think about it as just essentially clustered storage that's there. It's automatically spread across 3 availability zones for you, and you have multiple storage nodes in each one of those. Okay? So when you're creating your application, it's going to create each one of those storage nodes. And inside of that, when you ask for something, it's going to create 10 gig segments in each of those storage nodes. Right? And that'll automatically scale for you up to the 64 terabytes that Kevin mentioned. Right? And then when you have your applications across multiple availability zones, we're all connecting to the read-write nodes. And it's just going to write the transaction log records out to storage. Right? No need to do the flushes out of the actual data pages itself. Aurora Storage is handling that for you. Right? And it's going to write it out to those 6 individual storage nodes, as we were talking about. It's going to read those blocks back. It's going to try to get it from the local availability zone, where it's going to be faster. It keeps track of what the highest transactions are, so this way you're getting back the right versions. But in the event that something happens to one of the storage nodes, one of the segments didn't get the last updates, for instance, right? We did 4 or 6 for the quorum. One of the 6 never actually made it there. Network blip, whatever, right? We understand in the world of computing, nothing's perfect. So something didn't get there. That's where the peer-to-peer gossip comes into play. It'll automatically get it from one of the other storage nodes that have the latest version. The Postgres engine itself doesn't have to be able to repair it. Aurora storage is going to self-repair those for you. Postgres doesn't need to worry about that. Again, doing less work, Aurora storage is dealing with that. Right? So in the event that a whole storage node goes down, some of your data is on one of those storage nodes, the whole thing goes down. Again, Aurora storage will automatically take the different segments that were on that storage node and replace them into other storage nodes, completely transparent to you in the application. And then when you're speeding up a read-only replica, right, a read-only node, right, when you're doing that in Aurora Postgres, you need to be able to make a whole copy of the data. In Aurora Postgres, you have shared storage. There's no need to be able to create that copy of the data. It's just going to pull that back from the stuff from the shared storage. And there's going to be a little bit of communication between the read-write node and the read-only node in order to be able to sync up the caches and really invalidate the caches that are there. And you could create many of them, more than 1, 2, 3. You can create up to 15 read-only nodes. So this way, in the event of a failure of the read-write node, you could just go ahead and it'll just go ahead and automatically promote one of your read-only nodes. So going a little bit further into why 4 or 6 quorum, right? Why did it go along doing that? So when you're talking about RDS Postgres, we have multi-AZ, you have synchronous replication from one availability to a second one. Why didn't we just do the same thing with Aurora? Right. So inside of RDS Postgres, we do a commit, it gets flushed out to an EBS volume, comes back, great when you're talking about a single availability zone. Really under the covers, you're making 2 copies of it. Question back there? We'll get to that. We have slides for that. Yep. Right. So under the covers, EBS isn't just writing out a single copy of it. It's also backing itself up, or it's making another copy of it. So when you write it out to an EBS volume, it's also synchronously writing it out to a secondary, right? And it has to come back, acknowledge it, and then go back. So this way, you're already getting multiple copies of your data with EBS. But in the event that the entire availability zone goes down or that instance goes down, you want to have it in a second availability zone. Right? So you go ahead and create a second one. Great. But really for things like Aurora, you want to have even greater availability across multiple availability zones. So why didn't we just add a third one compared to what was there? Right? So when you do a commit, when you're talking about the multiple availability zones, it has to get synchronously flushed out to the secondary and the tertiary, right? And the local availability zone is writing things out to the local EBS volumes. It's going ahead, right? The secondary is kind of progressing a little bit more. Maybe the tertiary was a little bit further away geographically. It took an extra fraction of a millisecond for it to get there. So it's a little bit slower starting the work of flushing everything out to the EBS volumes. Right, so we acknowledged back from the local availability zone, right? Finally, we get it back from the secondary, but we're not done yet, right? We have to wait for that tertiary to finish in order to get all 3 availability zones all synced up synchronously, right? So what happens if you actually lose an individual availability zone or that instance, that tertiary instance goes down? We have to fence that off, right? So this way you don't do any writes to it while it's repairing itself. Right? So all the writes would go to the primary and secondary, and when the tertiary comes back up, it has to catch back up again, right? And it has to do, Postgres would have to do all the work of being able to do that. Right? But we did testing of looking what that would look like under a write workload of having 2 copies versus 3 copies, the 2 copies being what RDS Postgres does today. Right? So at the 50th percentile, right, difference between 2 and 3 replicas is 6 milliseconds versus 7. Really not that big of a difference. If you wanted that extra availability, great. You're giving up 1 millisecond, big deal, right? And even as you go 90 or 99.9, you might be able to do that trade of 22 versus 28. But that 99.9, that 1 in 10,000 transactions, is 4 times longer. You get a lot of jitter, right, of things that are there. So this way, that model won't work. As you add more and more synchronous replicas, you get more and more of that jitter. You have more of the possibility of one of those transactions going slow. Right? So it doesn't really work. Which is why the 406 quorum smooths out that jitter. Right? So when you do a commit, Aurora is going to push it out, so all 6 of them, all at the same time. Right? And he's going to get back things most likely from the local availability zone first. Right? And then you're going to wait from 1, you get back 2. We got the 4 of 6, we're done. We don't have to wait anything from that 3rd availability zone. We have 4 of 6 already committed, right, and gave us the acknowledgement back. Right? And then finally it'll come back, great. Right? So in the event that it missed one of those, Aurora Storage is going to resync that stuff. The engine doesn't have to wait for it. So to give you an idea of just getting rid of some of that jitter, did another test using pgbench. Right? We have things like, over the course of 20 minutes, not a very long test, of response time in milliseconds. Aurora gives us a nice even flow across the bottom there of nice, very low jitter, whereas Postgres, with a single AZ, not even going multi-AZ, we get all these jitters. So if you look at the bottom of that blue line, it's fairly close to Aurora. Right? Not that big of a difference. Right? But that jitter going up and down all over the place, those are checkpoints. Right? Periodically, every couple minutes, you got to flush out all your data pages and do a lot more work, starving the rest of the system from just flushing out those individual transactions. Right? So whenever you do a load test on a traditional database, you're going to see that wave action. Whereas Aurora, you're going to see a nice flat line. Right? So even at the very high, that low point there, you're not going to see that big of a difference between RDS Postgres and Aurora Postgres. Typical thing I see as people are benchmarking RDS Postgres versus Aurora. Let me do a single AZ on RDS Postgres, spread out my checkpoints to 60 minutes, and then run it. And hey, look, they're all about the same. Why would I use Aurora? It's because they haven't done checkpoints. Once you start doing checkpoints, all of a sudden you start seeing that, and the averages go way off. Question?
Real quick, when you do these tests, are you co-locating the application that's inserting these on the
same availability zone? Yeah.
So it's not a client somewhere.
It'd be on a client, but in the same availability zone, so we don't get the latency between the engine driver and the main database server itself. Right.
Are these because of like fundamental changes that you've made to the Postgres engine, or is it more just the way that you've architected it?
It's architecture around pushing a lot of the work that you would normally do. The Postgres engine has to do with the background writer, flushing out the data pages and doing checkpoints, of taking that same essential work and pushing that down into Aurora Storage. So instead of having one giant checkpoint, you're doing all that work of coalescing those data pages across many storage nodes. You're doing it in parallel and not impacting the main engine itself.
You're parallelizing your extents core RDB method.
Yeah.
The same fields it looks like Postgres.
Right. So you're only writing out those transaction logs, and then Aurora Storage takes everything else that Postgres would normally have to do and does it in parallel across many storage nodes. Right. So talking about the replica and clones, which we had a question about. Right. So in Postgres, when you need to be able to create a replica, so RDS Postgres, you ask for a replica. We take a snapshot of the EBS volume, move that over to a new EBS volume, spin up a Postgres read-only node and attach it to that EBS volume, right? And then we have to catch up. So that might take hours, depending on the size of your database and how many transactions are going through your read-write node. Right? If it's a very heavily loaded system, it might take a long time to be able to catch back up again. Right? So as you're doing updates, in Postgres, whether it's going to be community Postgres or RDS Postgres, when you do an update, you need to be able to write that out to the EBS volumes, but you might have to actually read that block into memory first in order to be able to update that. Right? And then once that comes back asynchronously, it's going to go send out that log record out to the read-only node on Postgres. And again, it has to do the same amount of work. It might have to pull that log off of storage in order to be able to update that and flush that back out to disk again. Right? With Aurora, your read-write node flushes things out to Aurora storage. The read-only node reads things off of Aurora storage. So when you do that update, the read-write node does the same thing that would with regular Postgres. Might have to read that block out of storage in order to be able to update it. It'll then send that asynchronous replication request out there, and it doesn't have to do anything to storage. If that block is in memory, it just invalidates that block, but it doesn't have to make any changes because you have shared storage between them. It doesn't have to duplicate that change the way it does with traditional Postgres. So just as an example, pgbench is one of the common benchmarking tools that the Postgres community uses. It has simple 4 tables. It's supposed to represent a banking application with accounts, tellers, branches, and history. And one of the nice things about that, question? Okay, yeah, the question is if we're getting everything out of Aurora storage, why do we have to send that asynchronous replica? Because that replica may have that block in memory, in page, so we have to invalidate that so it gets the latest version out of storage, right? So we have to send that invalidation message so it knows that it's no longer valid. Yeah. Sure. So, one of the nice things about pgbench is that we could do a read-write test where it's going to touch all the tables, or a read-only test where it's just going to touch the account tables, right? So if you're running that, it's just going to run a lot of selects across the accounts table, right? And we'll do our asynchronous replication from the read-write, sending all its changes out to the read-only node, right? And it'll apply it there. But when it's doing that, it's going to have to pull all 4 tables into memory. Right? It has to, in order to be able to do the updates, it's going to have to pull all that stuff into the read-only node in order to apply all those changes back into storage. Whereas with Aurora Postgres, since it's only sending those invalidation messages, right, it's just going to do the in-memory updates for the things that happen to the accounts table. So here's a graph that'll kind of illustrates that a little bit. So that orange line is your transactions. Right? And what happened at about 23 or 24 minutes or so, we did an update of the pgbench history. We did a backfill of it, updating all the rows. Right? We had to populate a value in there, which happens sometimes in production. You roll out some new functionality, and you have to update everything. You add a new default value of some sort. And what happens at that point when you're talking about Postgres, all of that has to be replicated out to the read-only node. So that green line is the replication lag. So things were going along great, it was keeping up, and then when you did that giant update, all of a sudden things started lagging, right? Quite a bit. This is in seconds, right? So that's up to 600 seconds. So your lag started going up to about 10 minutes. So instead of things being there in milliseconds, being basically up to date, that giant update all of a sudden made your replica just wait for that giant update to get consumed, right? Because all your updates have to happen in order. We're an ordered database. Everything's transactional, everything all happen in the same order. So nothing else could go through until that giant update has been processed by the read-only node. But in Aurora, we did that same backfill, and you don't even know there's a difference. right? And if you look at this, this is in milliseconds. So this is, lag is going along in about 10 milliseconds. Even when we did that backfill, it's down to about 1 millisecond. Because that pgbench history isn't being accessed on that read-only node. The messages go over there and just get discarded. Right? So it didn't have to do any processing. So one of the other cool features is cloning, creating a fast clone. So whereas replicas, you're doing things in order to be able to create it so this way it keeps up to date with the primary read-write node. Clones, you're creating something that's completely separate. So you might have a reporting application that every night at midnight you have to kick off reports from yesterday. Instead of having a read-only node trying to keep up over the course of the day, spin up a clone at midnight. And what that does is it creates its own read-write node, a completely different instance, right? But it's going to be accessing clone storage. So if you have a 20 terabyte database, you don't have to make an entire copy of it. What it does is just creates pointers out to the main data itself, right? So you're not paying for that extra 20 terabytes, right? You're just creating that clone storage, right? So that 20 terabytes comes up really quickly, really as quick as it takes in order to be able to spin up the instances and attach to the clone storage, right? So when the application starts interacting with the node, it's going to, when it asks for a block, it's going to pull it off of that clone storage, that pointer, and it's really going to pull it off of that main storage. Question?
What if I make writes or changes to the clone storage? Will that be propagated to the primary storage?
No, you'll see that in a second. Right? So the question is, what happens when we make changes? Right? So if we go ahead and make that change, what happens is a copy on write. So it copies that block from that main storage, brings it down to the clone storage. So this way you have two distinct copies of it, and it breaks that pointer link. Right? So this way, depending on as things diverge, you're going to have, you could potentially have duplicate of the entire database if you update all the rows in your database. But it's only going to do it as you start writing and making changes to that. You might insert new rows into that clone storage. It's just going to write it into the clone storage area. Right? Or from the main application, you start writing logs there, it's just going to write it out to the primary storage area. Right? Or if you make a change to it, it's going to do the same copy on write, flush out that old version out to clone storage, and write the new version in the primary storage area. So this way, when the instance that you take that clone, they're the same. All the pointers are out to the primary storage. But as you start making changes to either primary or the clone, it starts diverging. Right? That's why you're able to make those clones very quickly. If it's a read-only application, it's going to be what it was at that instance of when you took that clone. So you might be at midnight every day. So this way you don't have to worry about all the changes that are happening over the course of the day. Your database is good as of midnight. Right? One of the great things about this is as you want to test things on your primary database, maybe an update, you're rolling out some new DDL, you want to time how long it's going to take in order to create a new index, do it on a clone. You're basically doing it on production, right? Without having the overhead of restoring from backup, right? You're just doing it off a clone, right? And to illustrate, well, this way you could take essentially an instant copy of your production database and do whatever you will with it, as opposed to having to restore from backup, take a snapshot, restore from that, which will take a long time of duplicating the entire storage. With Aurora storage, we have intelligent storage. Good, Jim.
Another use case for that would be, for example, if you had to do some reports overnight, you might create a clone, then build an index on the clone, and that's not going to slow down your production system. And then you can go reporting here and then just
right. So it's right. Yeah, it's basically a near instant copy of your production database, and it'll run the same as your same production database. So that illustrates that here. Doing pgbench kind of throttled it at 20,000 TPS, right? And that's what that orange line is of doing 20,000 pgbench transactions. Right? And then we requested a clone at about 20 minutes, right? And then Grant, who did this test, kind of walked away and didn't keep track of when it actually started, but when he came back to his desk, he kicked off the same test on the clone about 20 minutes or so later, and it's doing exactly the same CPS. Right? You start up the same instance size for that clone, it's going to give you the same performance. It is essentially your production database, it's an exact copy that comes back very quickly. So going a little deeper on replication, right? So with logical replication, as Kevin mentioned in his talk before, we're taking the physical changes in the wall log, the transaction log, and converting essentially that into SQL statements, right? And with that, we could, do a lot of cool things with it. There's the logical decoding plugin, right, that allows different types of formats as it's coming out. Instead of getting out straight insert, update, delete statements out of your logical, you could also get those changes as JSON. So this way you could process it in different ways. A lot of the Postgres drivers, like the Python driver, the JDBC driver, supports reading the Postgres logical replication stream. So you could write it in that and be able to access your changes and just feeding it directly off that stream by essentially making a JDBC connection. Right? So what logical decoding works is by pulling from the main server itself. Right? And then you could take that application you've written in Java or Python and push that into something like Kinesis, right? Or it could go use DMS, which uses the same mechanism in order to be able to do that, to go to an RDS Postgres instance, could go to S3, could go to Dynamo, right? So this way it's change data capture off of your main database, being able to push that wherever you'd like, right? Or out to Redshift, what a lot of people do. You have your main OLTP database running on Aurora. You want to go deeper reporting out to a data warehouse running on Redshift. Okay. But one of the nice things in Postgres 10, right, is the ability to be able to do that without having something else in between. Right? So we had an EC2 instance, we had DMS that are sitting there. Postgres 10 has a publish subscribe mechanism, so this way Postgres could be able to talk directly out to the master server and be able to pull it out directly itself. So you could have, when this is released out into Aurora, and it's out in some private previews now, you could talk to the guy back in there in the corner if you want to have access to it. The better looking one. What you're able to do is have, as your changes are happening in Aurora, it could flow out into a community Postgres database. Maybe it's on-premise, maybe it's on EC2. So if you wanted to be able to leverage some of the stuff with Aurora, but still have an instance running some PLR or some PL Python, you're able to have your main transactions go through there and be able to run some of your reporting through PLR on an EC2 instance because you could subscribe off of the main Aurora instance, right? Or it could go out to an RDS Postgres instance or another Aurora instance, right? So cross-reading and replication. Question, go ahead. Right. Yeah, that's absolutely true. So the folks that originally wrote pgLogical, a company called Second Quadrant, they pushed that into the community. The community didn't take all of pgLogical; they took pieces of it. So yeah, you could use pgLogical to be able to do other things like replicating DDL, for instance. That sequences, yeah, and sequences. So there's other aspects to it. And Aurora Postgres and RDS, when Aurora Postgres supports logical replication, it'll support things like pgLogical the way we do with RDS Postgres. Yep. Mm-hmm. Yep. Mm-hmm.
So when would that, when will it be in order to do you guys have any information of people who have done something similar?
Yeah, that's definitely something that we could talk about offline. There's some folks here, whether it's Kevin or Dennis back there in the corner, about getting involved in some of the previews of that you'll be able to take a look at. And the best timeline I can give you is soon, right? But those folks can give you better timelines after the fact. Okay. Right. So cross-region replication, right? So you're running on US East. You're working for a company that requires a DR plan, right? So you want to be able to have everything running in another region as well. So what cross-region replication will do, it'll introduce two new things, a replication server and a replication agent that's sitting there at the storage level. So this way, when a transaction comes in, right, it's going to get pushed out to Aurora storage and validate the read-only nodes on the same region. It'll also push things out to that replication server. So that replication server will push things out to the other region in the replication engine, which will do the same sort of work that the read-write node and push everything out to Aurora storage, and also invalidate the caches in the read-only nodes in the other region. Right? So you can have the ability to have multiple read-only nodes on that other region. So if you want to have things that are closer to your customers, of being able to have reporting and other read-only queries running in a different region closer to your customer, you could have multiple of those. It also, in the event that you lose, some of the transactions get lost along the way, right? Again, Postgres itself doesn't have to do the work to catch it up. The replication server will pull things out of Aurora storage on the local region and be able to repair that on the remote region, right? So this way it doesn't affect your transaction throughput at all. So one of the use cases of that is if the region goes down, right? How does your business survive in the event that a region goes down, right? You could promote the other replica to one of them having a read-only node, right? And this way it'll happily you'll report your applications at that new instance, and away you go. Some other customers are using that as we roll out new regions. So you're running in US East, but if there's a new region that's more advantageous to your customers, being able to replicate out to the other region, so this way your switchover time is a lot smaller. You could replicate it, and this way, as you have a little bit of downtime to wait for things to catch up, you're able to do that switchover in a fraction of the time, as opposed to reestablishing that new region from a snapshot. Right? So this way, as we're adding more and more regions, as we're constantly doing, right, you could take advantage of those, of moving to a more advantageous region for your business. So caching. We're almost out of time here. In Postgres, you have when you're talking about RDS Postgres, we allocate about 25% for for Postgres and for the OS. And then its main cache, shared buffers, we allocate about 25%, right? Which is kind of standard practice in the Postgres world, if you read about that. And the rest is for Linux page cache, right, of about 50%. Right? So in the event that you're looking for something, it's going to try to pull it out of shared buffers. If it's not in there, it's going to try to pull it out of the Linux page cache. And if it's not in there, then it's going to pull it back from EBS storage. And it's going to have to go all the way back up the stack again of repopulating that. So you get duplicate buffers. You get double buffering for that 25% that's in shared buffers. Right? With Aurora, we have the same 25% for the OS and Postgres, but we allocate 75% for shared buffers. You're not getting that same double buffering because we're writing everything out to Aurora storage, not to the local file system. Right? But one of the advantages of being able to have that Linux page cache is the event that you have to restart Postgres because you changed your max connections. It doesn't get rid of that Linux page cache. Things are still in cache. So when you start that back up again, you still have a pretty warm cache. When you do that in Aurora Postgres, we didn't have that same benefit. So we had to create a new thing called survivable cache. So in the event that you have to do a restart or just you restart Postgres, your shared buffer stays there and you don't have to repopulate everything, right, with that survivable cache. Again, trying to speed things up a little bit here. Doing this for a pgbench of read-only scale of 22,000, right, which is a working set of about 350 gig, running on an instance with an R4 16XL, which has 488 gig of RAM, gives us that 75% cache. Is essentially everything's in shared buffers. And that gives us, in a read-only node, 689,000 TPS. It's a lot of transactions. It really selects that you're churning through really quickly, right? When we did that with Postgres, with a 25% cache, we're getting 417,000 transactions. Still really impressive numbers, but 1.6 times slower, right? So we were just limited by IOPS because of that double buffering, not everything was in RAM, right? So you read some of the Postgres community lists, they say, well, reduce your shared buffer size and use all the Linux page cache. When you do that down to 10%, it gets even slower. It's down 2x. Right? And that's because it has to do more work of checking shared buffers and then checking the Linux page cache to pull everything back out again. Right? So there's no double buffering there. But just to prove that Postgres does about the same, when you set that up to about 75%, you're doing 682,000 TPS, which is essentially the same as the number. So you get that same throughput of pulling everything out of RAM. There was no changes in Aurora Postgres for that particular use case, but you don't get that survivable cache. Right? I'm going to go for another couple minutes, and when I get to the performance section, I'm just going to stop because Jim's going to go deeper about that. One of the other features is cluster cache management. So what happens when you do a failover, when you want to be able to go to a new server, whether it's planned or unplanned? Goes along, you're doing a pgbench at 350,000 TPS, and then you have that failover at about 600 seconds. With Aurora Postgres, pretty quick, the failover time, 32 seconds. Problem is when you fail it over, you're at a cold cache, essentially. So this line here is the P90, so waiting to get back to 90% of what your transaction throughput is. In order to get the same cache level, right, it takes 340 seconds to get to that same performance number in order to warm that cache back up again. What cluster cache management does is it takes these different read-only nodes and you assign a priority to it, right? So priority 0 is the highest priority for a failover target, right? So all the old ones are 1. So this way, it'll prefer going to that failover priority of 0. And if you enable that with APG CCM enabled, turn it on, what it does is it sends the read-only node sends a Bloom filter request of here's everything that's in my shared buffers, right? The read-write node will respond back of okay, here's all the things address is all you have to load, right? And then it'll go ahead and start loading those things into memory, into shared buffers, and eventually it'll be fairly close to what the master is. The net effect of that is when a failover happens and when you have CCM enabled, that 340 seconds now goes down to 32 seconds because that cache is already warmed to what that master was. Okay. With that, I'm going to jump past all this, and I think that the last thing is the performance, and that's all. Jim will cover all that, and with that, questions. And this is a lot longer talk than 50 minutes. Thank you.